If there is a key to the universe, it may well be hidden within the cryptic message that comes to us from the stars.
When we look at the nighttime sky, it's obvious that the stars are of differing brightnesses. And the ancients noticed this too, and in fact Hipparchus categorized the stars according to their brightness. He called the brightest stars first magnitude, and the faintest stars that the eye could see sixth magnitude. Telescopes now extend the range of brightnesses of stars that we can see, so that in fact the faintest stars we describe are at 24th magnitude. And we can apply the brightness scale of magnitudes to objects that are brighter than the brightest stars as well. For instance, the sun. And it has a magnitude of about minus 26. Well, from minus 26 to plus 24 in magnitude is a range of about 100 million in brightness. And of course, it's a lot easier to use the magnitudes than to describe it that way. Now, the reason the stars differ in brightness from one to the next is for two reasons, actually. One, the distances of the stars, and two, their true brightnesses. Stars obviously are at different distances from us, and it's easy to imagine the effect of this by thinking of two light bulbs. The two light bulbs, say a 100-watt bulb and a 25-watt bulb, have different true brightnesses, or luminosities, as they're called. Well, the 100-watt bulb is obviously the brighter, but it could be moved to a far enough distance so that it would appear fainter than the 25-watt bulb. And the same could be true of the stars. Bright ones at a great distance could seem no brighter to us here on Earth than a fainter star, at least a star that was fainter in its true brightness or luminosity. Well, it's by measuring the luminosities of stars that astronomers realize that they are actually suns, but suns at incredibly remote distances from us. They're able to determine this, of course, to measure the luminosities, provided they can measure the distances. This was first done in the 1830s with parallax, and provided they can measure the apparent brightnesses of the stars, that is, of course, how bright they appear to us here on the Earth.
Looking up at the night sky, it is possible to see thousands of stars, thousands of points of light. We can see that some stars are bright, while others are faint. And in a few instances, we recognize color. But there is little else that we can learn about the stars with the naked eye. Looking through the eyepiece of this huge telescope, the stars are still just points of light, some bright, some dim. Tonight, these points of light are distorted by atmospheric effects into disks that shimmer in the eyepiece of the telescope. We can observe millions of stars with this instrument, stars that belong to our Milky Way galaxy. Beyond these stars in the Milky Way, we can see other galaxies, other systems of millions of stars, systems that appear in the telescope as hazy patches of light. Our Milky Way galaxy is very much like this galaxy. Photographs of the same galaxy taken through the telescope reveal much more detail than can be seen visually through the same instrument. This is roughly the way our own galaxy might look at the distance of a few million light years. If we wanted another view of our galaxy, it might look like this galaxy, which is seen edge on. The photograph reveals only a flattened system of stars with a central bulge. However, in our Milky Way galaxy, we know that there are many other stars that surround this flattened system, forming a sort of halo. If we could photograph the faint halo stars, the photograph might look like this illustration. The fascinating question is why the Milky Way galaxy assumed its shape and how it was formed originally. Studying the motions of stars in the halo, as well as the plane of the Milky Way galaxy, allows us to follow their present motions far back into the past and thus gain insight into the conditions under which the stars were formed. But the luminosities, or intrinsic brightnesses of stars, are also a vital link to understanding both their past and their future. To determine a star's luminosity, however, it is first necessary to measure its apparent brightness. This astronomer is measuring the apparent brightness of stars with the 24-inch telescope at Lick Observatory, a very sensitive photoelectric photometer, which converts light energy from a star into a tiny electric current, has been attached to this telescope. First, a star is identified in a finding telescope. Next, its image is isolated from the other star images in the field by means of a diaphragm. The light from this single star then passes into a photomultiplier tube, which produces a weak electrical current proportional to the light energy received. The signal is amplified and is finally displayed on a chart recorder. The farther the pen moves to the right, the greater the apparent brightness of the star. While the tracing fluctuates due to atmospheric effects, we can nevertheless get an accurate reading by averaging over suitable lengths of time. Much additional information can be obtained by measuring the star's apparent brightness in different colors. Filters, which in this case pass yellow, blue, and ultraviolet light, are inserted in the beam of starlight that passes through the telescope to the photomultiplier. From such multicolor measurement, the surface temperatures of stars can be determined as well as their apparent brightnesses. If we know the distance to a star, and this can be measured for nearby stars by a standard surveying technique, we can calculate the real or intrinsic brightness of similar but more distant stars, and incidentally, their actual sizes. Based on the measurements, we can imagine how stars might appear from a vantage point in space. You would see a great number of dim red stars with relatively low surface temperatures and that produce 1,000 times less light than our own sun. We would find many stars very much like our sun, with surface temperatures around 6,000 degrees. We would also find bright blue stars with surface temperatures around 50,000 degrees. These stars are thousands of times brighter than our own sun. Most of the stars in the sky can be arranged by surface temperature and intrinsic brightness into a continuous series that astronomers call the main sequence. The bright blue giants lie at one end of the sequence, the dim red dwarfs at the other. Off this main sequence, there are some immense red giants. As their colors reveal, they are cool stars. They probably began as bright blue stars, and in an evolutionary process of aging, their surfaces have cooled and they have swelled to their enormous sizes. Most of the stars in the heavens shine with a constant brightness because there's a balance between the force of gravitation that acts to contract the star and an elastic or pressure force that acts to expand it. Measurements of apparent brightness such as these have also led to the discovery of other stars, stars that are not constant in light output. Often in studies of stellar motions, astronomers make use of these variable stars. They are relatively rare and must be found by systematic search procedures. With a 20-inch astrograph, this astronomer is taking photographs of remote regions of the Milky Way to locate the variable stars in those regions.
Well, the variation between brightness with distance is something that changes in a very predictable and understandable way. And so if we know the true brightnesses of stars and their apparent brightnesses, we can get their distances. The apparent brightness is easy. We can get that simply by looking at the star. And for some exceptions, rare exceptions, we can know the true luminosity. The Cepheid variables, for example. By watching their changes in brightness, we can know how truly bright they are. And so we measure the distances. We can also measure distances in independent ways, and by using those distances and the apparent brightnesses of stars, we can then determine how bright stars truly are, their luminosities. And what we discover is that the range of luminosities is widely varying. In fact, it's dramatically varying from stars that are millions of times brighter than the sun to stars that are in fact 10,000 times fainter than the sun. We can use the magnitude scale to describe these differences in brightness, and in fact then the brightest of the stars are at about -10, and the faintest stars are at about +15. If we were to try to put the sun on this same scale of absolute magnitude, well, we'd have to put it out at a distance of about 30 light years. That's relatively close as far as the stars are concerned. And at that distance, the sun would appear to be a 5th magnitude star. not particularly bright. In fact, one of the fainter stars in our sky, barely detectable, in fact, to the human eye. Well, the stars are very faint, and that's why telescopes are extremely important. Telescopes act like giant funnels that gather the light, and as they do that, astronomers observe the light, perhaps photograph it or measure it in some other way, and so through these processes learn something about the stars. A telescope, like the 200-inch, is equivalent to having an eye 17 feet across.
The giant 200-inch Hale telescope on Palomar Mountain is part of the largest laboratory for astronomical research in the world. With photographs taken by the telescope, the stars are studied with a variety of instruments. One, a photographic densitometer, is used to measure the density and diameter of the star's image. The iris of the densitometer measures the size of the star's dot on a photographic plate and converts the reading to a number by which astronomers can judge the apparent brightness of the star.
By the mid-19th century, astronomers had measured the brightnesses and distances for several of the nearer stars. And they realized then that the stars were actually suns, but suns located great distances, incredibly great distances from us here on the Earth. And even though they knew brightnesses and distances, there was really little else they could say about the stars. Their techniques didn't allow them, for instance, to know what the stars were made of, or for that matter, how the stars were born, how they managed to shine today, and how they might eventually die. Another tool was needed to solve those problems, and at about that same time, a new tool, spectroscopy, was developed and applied to the problems of astronomy. Now, people had speculated about the nature of light at least since the time of the ancient Greeks and Pythagoras, but it wasn't until the 18th century that Sir Isaac Newton first separated white sunlight into its rainbow of component colors with a prism. Now, when we look at this rainbow of colors, it appears to be simply a smooth blend from one color to the next. But by looking at it more carefully with a spectroscope like this, we're able to see a lot more detail in it. We're able to spread that rainbow of colors out. And what we discover is that it is crossed with numerous dark lines. Well, these dark lines, these dark spectral lines, were discovered in the 1800s. They're called Fraunhofer lines, and they contain a great deal of information about the star. We can tell, for instance, from the spectral lines, how hot the star is at the surface, its temperature, and its pressure as well in the atmosphere. We can tell what the star is made of, that is, its composition, and whether the star has a strong magnetic field. We can also determine if the star is spinning on an axis and if the star is moving, and if so, in what direction and how fast. This last piece of information is obtained with the Doppler effect. The Doppler effect causes a star to appear a little bluer if the star is moving toward us, or a little redder if it's moving away from us. Now, actually, this change or shift in color is too subtle to really notice, but the Doppler shift also causes the lines in the spectrum to move toward the blue if the star is moving toward us, and again toward the red if away. Well, careful measurements of the shifts in these lines allow us then to determine whether the star is moving, if so, how fast, and of course, in what direction, toward or away.
This is Lick Observatory on Mount Hamilton near San Jose, California. In a complex sequence of events, starlight is directed from the telescope to a spectrograph. The faint light from a distant star is gathered by the huge 120-inch diameter mirror and reflected toward a point of focus near the top of the telescope. The converging beam of starlight is then intercepted and reflected by a second mirror back down the telescope tube. A third mirror reflects the beam through the polar axle of the telescope down to this room. The viewing telescope, which is used to identify the star and center it in the field of view, is withdrawn, and the beam of starlight crosses the room to the opening or slit of the spectrograph. The polished jaws of the slit reflect some of the light back to a guide viewer. Most of the light passes through the slit and enters a room where it is reflected by a collimating mirror to a diffraction grating. This grating is an aluminized flat mirror of upon which many parallel microscopic grooves have been ruled by a precision instrument. There are 15,000 grooves per inch on this grating, which disperses the light of different colors, rainbow fashion, into slightly different directions. This dispersed light is intercepted by a camera mirror and focused to produce a band of pure colors or wavelengths called a spectrum, which in this case is recorded on a photographic plate. The photographic plate has been loaded in complete darkness in a plate holder, which is placed in a camera. Again, in complete darkness, the slide is pulled and the plate is ready to be exposed. The targets tonight are all variable stars. A discharge tube provides a set of standard spectral lines of a light source not in motion. The standard spectral lines are recorded on the same photographic plate as the spectrum of the star. The stars being measured are very far away and therefore very faint. Exposure times as long as 1 or even 2 hours must be made. During this time, the atmosphere continually plays tricks with the image, changing its apparent size and deflecting it in different directions. So an astronomer spends much of his night guiding the telescope to be sure that the beam of starlight is entering the slit of the spectrograph at all times. When the air is very turbulent, or when there are clouds, and it's impossible to observe faint stars, viewing can be frustrating. But when the clouds have passed, when the air is clear and calm and the star images are not dancing or twinkling but are steady, the end of the night comes all too quickly. Part of the night's work is developing the plates, and finally you see the results of your effort. The dark vertical lines at the top and bottom of the plate are the standard spectral lines of the discharge tube. Across the center of the plate are the spectral lines of the variable star. The difference between the positions of the standard lines and the lines of the variable star, the Doppler shift, will be measured carefully later to give the speed at which the star is approaching or receding from the Earth.
The radial velocity of a star, how quickly it's moving toward or receding from the Earth, is not the only information stored in the spectral lines. Each spectrum is actually a stellar fingerprint, which can reveal the identities of the chemical elements which make up the star. Each element produces its own particular pattern of lines. Well, spectroscopy proved, for the very first time, in fact, that even the most distant stars were made of the same elements that we find in the sun and in the Earth, or for that matter, even in ourselves. But many other things affect the appearance of the spectrum besides chemical composition. The patterns of the lines, their shapes, and their darknesses all contain other information produced by these effects. And so in order to separate out the chemical composition of a star, we need to have the help of some other ingenious equipment.
Steve Naftalan studies the chemical elements contained within stellar atmospheres.
Stellar spectrogram is a photographic recording of the spectrum of a star. We pass light from a star through a prism or reflect it off a grating, and it disperses it. It spreads it out depending upon the wavelength of the light. We record that on a photographic plate or directly onto a computer tape. Later we can reproduce this, and we call this the spectrum or spectrogram of the star. Here are some examples of a spectrogram of a star. In some cases, it's extremely small, such as this one. It's just a small smudge on a plate. Others are somewhat larger in size. And occasionally we even have some that are as large as the entire photographic plate. None of these, however, are large enough for convenient viewing. We have to look either through microscopes or use machines to trace the spectrum. When we make a spectral tracing, we use various machines to enlarge the spectrum and to record it on paper or on computer tape. We then can look at these tracings in detail and notice the various features on the tracings. For example, this is a spectral tracing of a particular star, and each of these particular dips in the spectrum represent the absorption by various chemical elements in the atmosphere of that star of light at this particular wavelength. These are called spectral line profiles. These are called absorption lines. Each of these can tell us information about the nature of that particular star. The spectrum that we have here was taken with what's called the spectrophotometric scanner at the Cassegrain Focus at Lick Observatory, and it looks to our eyes almost identical with the spectrum that we would obtain with a photographic plate. However, there are several advantages. The prime advantage, perhaps, is accuracy. This was done with a photometer, and as such, it's an exact reproduction of the energy output of the star, whereas the photographic plate is only relative energies. This is considered more accurate, and for certain purposes, it allows us to do more analysis. It's also somewhat faster to obtain, and this is good because we have limited access to large telescopes and limited amount of clear observing time. In order to obtain the abundance of elements from these spectral tracings, we need to analyze the strength and shape of the spectral line profile. This is a computer printout of spectral line tracings, and each of these represents an absorption line in the atmosphere of that particular star. The stronger the absorption line, the larger this line is, the more abundant that element might be in the star. But there are many other effects, such as temperature, surface gravity, rotation, and so on, that can also enter in. There are so many effects that it's almost impossible to remove all of them by hand, so we use the help of a computer. These are computer printouts where a computer has attempted to reproduce the observed spectral feature, and each of these represents a different attempt with slightly different profiles dependent upon such things as temperature, turbulence in the atmosphere of the star, and so on. Ultimately, we hope to be able to reproduce the observed spectrum. This is a graph showing the observed spectrum of a star and various computer attempts to reproduce that spectrum. When we have successfully done this, we feel we have an accurate estimate of the abundance of various elements in the atmosphere of that star. When we look at the line profiles of a star, we're able to deduce many various characteristics of that star. Primarily, the first thing we always look for is the temperature of the star. After we have determined the temperature, we can then determine the value of the surface gravity, the strength of gravitational force at the surface of the star. We can determine the rotation rate of the star. We can determine how much turbulence there is in the atmosphere, the abundances of various elements in the atmosphere of that star, and frequently even other parameters dependent upon the quality of the spectrum.
The ability of a chemical element to absorb certain colors and create dark spectral lines is critically dependent upon the temperature of the stellar atmosphere where the chemical resides. So the particular pattern of lines which appears in the spectrum of a star indicate the star's surface temperature immediately. Elements such as hydrogen, helium, calcium, and iron each have their own optimum temperature for creating spectral lines. If a star's spectrum reveals lines of iron, for example, then iron must be present in the star. But since all stars are made of much the same chemicals, the absence of iron lines probably only means that the temperature was not right for them to appear. Therefore, astronomers classify the spectra of most stars into 7 spectral classes: O, B, A, F, G, K, and M, based on the pattern of their spectral lines. And these spectral classes indicate temperature. O stars are the hottest, at some 40,000 degrees, and M stars are the coolest, with surface temperatures as low as 3,000 degrees. The star can now be plotted on a chart as familiar to astronomers as their ABCs. The Hertzsprung-Russell diagram. It was in the early 1900s that Danish astronomer E.R. Hertzsprung and American astronomer Henry Norris Russell discovered that stars fall into certain patterns according to their brightness and color. Like spectral class, color also indicates temperature. A red star is cool. A blue star is hot. By substituting our sun for the protostar, we can follow its life cycle on the HR diagram. Deep inside the protostar, the pressures mount. Temperatures rise. Suddenly, hydrogen in the core ignites, and in the violence of nuclear fusion, our sun is born. It is on what is called the main sequence now, and will remain there for millions of years. It has become a G-type star. Its age is 4.5 billion years. As the sun's surface boils from hydrogen burning, it increases in brightness. The sun's composition is changing now. Hydrogen is converting to helium. The diameter is increasing. Temperature is decreasing. 80 million years after leaving the main sequence, the sun changes abruptly. It expands 200 times, engulfing Mercury, Venus, and the Earth. The helium ignites. Astronomers call it the helium flash. With the change of fuel, strange things happen. The sun becomes unstable. Pressure is expanded. Gravity contracts it. It pulsates and becomes a variable star. There are many other types of variables. Some pulsate once a year, others in a few seconds. Having passed through the variable stage, the sun becomes brighter, 10,000 times brighter than our present sun, expands 300 times larger. It has reached its maximum size and is called a red giant. As the supply of helium diminishes, the sun contracts. Deep inside, the crush of gravity changes the structure of atoms. Heavy elements are formed and ignite. Now temperatures soar, reach well beyond 1 billion degrees. Decreasing in size and in brightness, the sun enters its last phase. It becomes white and small, only 1/100th the size of our present sun. This white dwarf begins the long, slow process of burning out. Invisible, it will wander through space. The only energy remaining is that which formed it, gravity. Stars are the living record of the universe. They provide clues to the past and future of galaxies, including our own. Of all the stars which illuminate the night sky, less than half traverse the depths of space alone. Most, in fact, are constant companions to other stars.
You usually think of the stars as simply being single objects, perhaps accompanied by a family of planets, but otherwise alone as they make their way through the galaxy. However, if we look at the sky, we see that at least some of the stars do appear to be double. In fact, one of them is the second star from the end of the handle, the Big Dipper, off in the northern sky. That star is known as Mizar, and if you look at it carefully, you probably can see that there is a companion star, a very faint one nearby it, known as Alcor. In fact, sighting this star was used as a test of the ability to see in ancient times. At least